Welcome to Chem Help ASAP. This is yet another reaction video. Again, I'm going to react to an old NileRed video. When I say old NileRed video, it's 10 years old. He has some great old content that's just straight up organic chemistry. If you haven't looked at older parts of his catalog, please do. This particular video has NileRed making chloroform from just acetone and bleach. I have made one change for this video. Some people have asked for more theory background, and I've tried to incorporate that into this video. I think you'll know it when you see it. If you can think about it, if you like it, please let me know. If you don't like it, let me know, so I can add more, I can cut that out. Anyway, let's get into NileRed's preparation of chloroform.
Historically, chloroform was widely used as an anesthetic, but nowadays it's mostly used just as a solvent. Interestingly, it can be easily made from common household products. In this experiment, the major chemicals I used were 3.6 liters of concentrated bleach and 100 milliliters of acetone.
Now, I would have never thought of making chloroform from bleach and acetone. And those are two very available reagents. Of course, I work in a research lab where if I want chloroform, I can order chloroform. I don't need to make it. So, but still, this is a really clever way of getting chloroform. Note that he is using someone else's procedure. This is from YouTube user UC235. Unfortunately, when I check this channel, the channel does still exist, but all the content has been pulled down. That's kind of a loss. I'd like to see the original procedure.
The first thing that must be done is to determine the concentration of sodium hypochlorite in the bleach.
Okay, so he's going to use bleach. Bleach is not pure sodium hypochlorite. It is a solution, and that solution has a concentration. If you look on the side of a bottle of bleach, it'll tell you the concentration. But I wouldn't trust that concentration, and I don't think NileRed trusts that concentration. So to figure out exactly what the concentration is, he's going to do a titration. But bleach does decompose over time, so it may not be as strong as the bottle says. So he's going to do this titration setup and figure out the exact concentration.
This is done by reacting about 5 milliliters of bleach with 3% hydrogen peroxide.
Okay, before he starts, so you can see the equation across the top. He's reacting hydrogen peroxide, H2O2, with sodium hypochlorite that's in his bleach solution, and that's what's in the bottom of that flask that he's getting ready to open the stopcock on. It's over on the left. And that's going to form water, sodium chloride, as well as a gas, O2 gas. And through that amber tube, he's going to bubble that gas up into that graduated cylinder, and that's going to force water down out of the graduated cylinder, and he can measure the change in volume, and that change in volume tells him how much oxygen he's formed. And so this is kind of it's a titration of sorts. It's an M1V1 equals M2V2 type calculation, and then he has to throw in a little perfect gas law, which he'll describe. This is, I would love to see how he set up that graduated cylinder, that inverted graduated cylinder. If I were trying to do that, I think it would take me a couple tries, and so I'm guessing it took him a couple tries as well.
As shown in the equation above, the hydrogen peroxide reacts with the sodium hypochlorite to form water, sodium chloride, and oxygen gas.
Let's just go backwards a bit. I was expecting little fizzy bubbles, and those are big glug bubbles, so
Reacts with the sodium hypochlorite to form water, sodium chloride, and oxygen gas. Hydrogen peroxide is added until no more bubbling occurs and the reaction is complete. The level of the water in the graduated cylinder is measured before and after the addition of the gas. By calculating the amount of gas that is evolved, and on the assumption that 1 mole of gas occupies a volume of 24 liters, we can calculate the concentration of the bleach.
So there's a perfect gas law coming in, 24 liters per mole. I am impressed with how much gas was released. I thought it'd be a small volume change. That's a lot. From just 5 milliliters of bleach. That's impressive. So as you can see, he calculates a concentration of about 1.28 molar of sodium hypochlorite. There is one big variable in here. He's using 3% sodium peroxide. I'm sorry, 3% hydrogen peroxide. I'm not sure I trust that 3% hydrogen peroxide value either. So, in the end, you have to assume some number is correct. And, you got to trust something. So he's going with that 3%, but that 3% can be off as well.
The equation that I used is shown above, and the result I obtained was that the sodium hypochlorite concentration was about 1.28 molar.
Did you see? He added a few more drops at the end just to make sure adding more hydrogen peroxide did not generate more gas. So he knows that he has exhausted all the sodium hypochlorite in the bleach solution in the bottom of that flask. So he knows he's gone past the end point. Now, I want to talk a little bit about the theory of this reaction. So let's change up the slides a little bit. All right, let's talk a little bit about this reaction. We are going to start up at the top middle with acetone. And acetone has hydrogens on its alpha carbons. Now, in bleach contains a lot of base. Base helps, sodium hydroxide, it helps stabilize the bleach. It extends the shelf life. And that base can remove some of those alpha protons, just one at a time, and form an enolate. That enolate is a good nucleophile, and it can react with sodium hypochlorite. I don't want to try to figure out exactly what form of sodium hypochlorite reacts, but some form of it does react, and this acts as a source of electrophilic chlorine. And so we attack, and bam, we've put one chlorine on there. Let's do this a couple more times. Once we have chlorine on, we still have more alpha hydrogens, and these can react with sodium hydroxide. Sodium hydroxide can do a deprotonation of one of those remaining protons. That will form yet a new enolate. And that enolate actually forms a little faster. This is a little bit more, this chlorinated acetone is more acidic because the resulting conjugate base, the enolate, is stabilized through an inductive effect by the presence of that one chlorine. Now that enolate also can react with electrophilic chlorine. And now we have two chlorines on here. We're going for 3, so we got to do this one more time. Now we have dichloroacetone. We still have one more alpha hydrogen. Sodium hydroxide can deprotonate that to make a new enolate. This enolate is even more stabilized because we have 2 chlorines attached to have a stronger inductive effect. The fate of that enolate is the same. It will react. There's a lone pair of electrons. It will react. And now we have our 3rd chlorine on here. Looking good. Okay, so now something different is going to happen. Now we have 3 chlorines. We no longer have a hydrogen on that alpha carbon, but there's something sodium hydroxide can do. Sodium hydroxide is a nucleophile. It's not just a base, it's also a nucleophile. It's electron rich. And it can attack the carbonyl carbon. Anytime we attack a carbonyl carbon, we get a tetrahedral intermediate. And tetrahedral intermediates can potentially collapse, kick out a leaving group, and in this case, because that carbon bears all those chlorines which help pull away electron density and stabilize charge, we can potentially kick that out as a leaving group. Now that's going to form acetic acid plus this carbanion. Now, normally you can't make carbanions like this, but this is special because it has all those attached chlorines that stabilize that negative charge. If this does form, it will react with the water in the solution. It will be protonated, and it will form our final product. And our final product here is chloroform. Now, if you're skeptical, you might say, hey, listen, I'm not buying this because sodium hydroxide could also attack in that first step. So let's go to the first step. Acetone certainly can be attacked by sodium hydroxide. That's a very valid point. And we can make a tetrahedral intermediate. The thing is, we can't kick out these methyl groups as leaving groups because they don't have chlorines on them. They're not going to be stable enough to get kicked out, to get ejected. So they are stuck. So what happens to this tetrahedral intermediate? It ends up kicking back out hydroxide and reforming the carbonyl. It's called a non-productive equilibrium. The same will happen with this carbonyl. We can form a tetrahedral intermediate, but one chlorine isn't enough. This is not a good leaving group. So the hydroxide just gets ejected and we go back to the carbonyl compound. The same happens on this compound. 2 chlorines is not enough, but 3 chlorines is. So once we finally put that 3rd chlorine on there, now we've stabilized that carbon enough so it can be ejected as a leaving group, and we can, after protonation, we can form our chloroform. So this reaction that we've drawn out, and the one that NileRed is performing, makes chloroform. You can do this reaction if you use bromine and you make bromoform. You can do this reaction with iodine and make iodoform. And so in general, people call this a haloform reaction because you can put the 3 halogens on a single carbon. So that's a little background theory of how this reaction works. It's a long process. In this reaction, there's a lot of steps that have to happen. And remarkably, they all do happen, and you can make chloroform with this reaction. So let's go ahead and see NileRed actually perform the reaction. Okay, so we're back to this titration. You've done the titration.
This isn't necessary, but I used the hydrometer to measure the density of the bleach, and I determined that the concentration was about 8.6%.
Now, so he also did a backup. He's like, I got this titration. Maybe he was questioning whether it was accurate or not. So he used a different method, hygrometer to measure the density of this solution. From the density, he determined another concentration as 8.6%. So, he's just got a backup method to see that does the titration make sense? Do I trust this titration? Apparently, this result helped him trust the titration so he could move ahead and do the reaction with more confidence.
The bleach was chilled to about -2 degrees Celsius and 150 milliliters was poured out. 150 milliliters is removed to make sure that it has enough space to add the acetone as well as to shake it. The reaction of bleach with acetone is extremely exothermic, and it's absolutely necessary to cool it to at least 0 degrees Celsius before.
Okay, so he needs this cold, and he needs a little bit more room in this bottle. So he's going to add 100 milliliters of acetone to this, and he needs some space in the bottle. So he's going to pour out a little bit of bleach to make space for that acetone.
For the addition. I added about 100 milliliters of acetone to the bleach, which represents an excess of bleach at around 11%. I think.
Now, if you go through the math, 100 milliliters of acetone has that's about 1.35 moles of acetone. And so that is his limiting reagent for this reaction. So if he put in 1.35 moles of his limiting reagent, and every mole of acetone can form a mole of chloroform, then his theoretical yield is 1.35 moles of chloroform.
An excess between 3 to 5% is better, and 11% is much too high. We use an excess of bleach because we want to make sure that all of the acetone is consumed. Any leftover acetone could form a difficult to separate azeotrope with the chloroform. After adding the acetone, the bottle is capped and shaken. The cap is then removed and placed lightly on top to allow any gases to escape. I left the bottle overnight to allow for a complete separation of the chloroform from the aqueous layer.
Now, if I were going to shake that up, I'd probably invert the bottle some. I would have probably shaken it up a little bit more, but I'll mention why that might be a bad idea in just a moment.
Chloroform is denser than water and immiscible, so it should form a layer on the bottom. After 5 minutes, the temperature is already at around 30 degrees Celsius. The temperature peaked at around 45 degrees Celsius. So this reaction, he started this at -2 Celsius, so it was pretty darn cold. And then he added the acetone, shook it a little bit, too little in my opinion. And then within minutes, it got up to 30 degrees and peaked at 45.
if I had been shaking that and I really mixed things super well, then maybe the temperature spike would have been higher and that might have been a bad thing. So, he is following someone else's procedure after all.
For the purpose of the video, I will visually demonstrate the reaction between the acetone and the bleach. When the acetone is added, it reacts with 3 equivalents of sodium hypochlorite to form chloroform, sodium hydroxide, and sodium acetate. After allowing the solution...
Let's go back to that. Okay, so this is the reaction that I walked through. I didn't show the stoichiometry so clearly, but there is, we start with acetone. It reacts with sodium hypochlorite. That's the reagent in bleach. It forms chloroform, which is trichloromethane. And we end up forming acetic acid, but under the basic conditions, that gets deprotonated to form sodium acetate. So everything we talked about is there, and we walked through that mechanism of the process.
Form sodium hydroxide and sodium acetate. After allowing the solution to sit undisturbed for a short period of time, it's possible to see chloroform in a separate layer on the bottom.
So that is a key idea. Chloroform is not very soluble in water, so it does, and it is more dense than water, has a density of close to 1.5 grams per mole. So it does sink in water, and you can see that in this kind of model reaction he has set up.
The solution is still yellow due to the presence of unreacted sodium hypochlorite. Carefully decant the upper aqueous layer.
I do like that he's using this broken beaker. You don't throw stuff away until it's broken beyond use. And that little, it's a pretty big chip in the top rim, but that's okay. You can still get away with using that.
Due to the large amount of water, you're going to need to do this several times.
So presumably he's let this sit overnight. All that chloroform has sunk to the bottom of that jug. So everything he's pouring off is just leftover bleach solution, aqueous solution. That's not what he wants, so he can dump that off and discard it.
You should empty the aqueous layer into a waste container labeled bleach and chloroform waste. Eventually, the remaining liquid of the bleach bottle is poured into the beaker, and the chloroform layer is allowed to settle on the bottom. You might notice that the solution is much less yellow than the previous example that I showed. This is because it was allowed to react overnight, and the concentration of sodium hypochlorite in the solution is much less.
Chloroform kind of behaves like this. It sinks, but it'll float on top a little bit. You just have to give it time for everything to sink to the bottom.
Leave it for several minutes until the chloroform layer fully separates. Decant off as much of the aqueous layer as possible and then add the rest to a separatory funnel. Allow the two...
So you can see there, well, it's hard to see in a static image, but there is a bottom layer, that is his chloroform layer, that's his desired product, and that top aqueous layer he's really not interested in. So he's using a separatory funnel, which is a great way to separate immiscible liquids to get his product out.
Phases to separate, and then drain the lower chloroform layer. Add the upper aqueous layer to your waste container. The chloroform was washed once with saturated sodium chloride, and then it was added to a distillation flask containing calcium chloride.
So he's washing this with saturated sodium chloride. That is something that can help pull out excess water. In my experience, it doesn't work great, but it is a way to try to remove water from an organic layer.
The simple distillation of the chloroform was carried out using a hot water bath. The distillate that came over below 60 degrees Celsius was cloudy and it was discarded.
So normally when I think of cloudy layers, cloudy organic layers, it's probably got some water in it. So there might have been some residual water. He's gotten rid of that material. No, there is a cost of getting rid of that material. His yield will be lower, but presumably the stuff that he does isolate later will be of higher purity. So you got to sacrifice some yield to get higher purity.
The temperature then remained constant at around 60 degrees and the distillate was collected as a clear liquid. The total volume of chloroform obtained was about 58 milliliters. The chloroform was transferred to a bottle that was wrapped in tinfoil to protect it from light.
Now that bottle, that is a bottle, the type of bottle you see in lab all the time. Notice how it has that kind of that plastic lip on top of those threads. That is a bottle, that's an old bottle that was used for like 500 milliliters of a strong acid. And so that's an old acid bottle, they tend to be strong bottles. They're great bottles for storage.
About 1 milliliter of absolute ethanol was added to stabilize the chloroform and prevent the formation of phosgene. Again, the final yield was about 58 milliliters, which represents a final yield of about 53%.
Okay, so that's a final shot. Note that that bottle now has a yellow cap on it. Yellow caps are used for sulfuric acid bottles. So that is an old sulfuric acid bottle. He got 58 milliliters. That corresponds to 53%. Let me look at my notes. 58 milliliters of chloroform is about 0.723 moles. So comparing that to our starting amount, which was 1.35 moles of acetone, that is a 53% yield. And I think that's great. He took a bottle of bleach and 100 mils of acetone and got a 53% yield of chloroform. I think that's pretty impressive. And now it's ready for storage, and he's minimizing decomposition because you certainly don't want to make phosgene as you store your chemicals. So that's the end. Thank you to a young NileRed, a NileRed of Christmas past. Thank you for your attention. And if you have any feedback or comments, please leave them in the comments section below the video. Take care.